everyone. Today, in this video, we are going to discuss the quantum wave function. Before going to the quantum wave function, let us try to have a basic uh, taste about the quantum mechanics. What is quantum mechanics? So, the classical mechanics is an approximation of the quantum mechanics, and the fundamental difference between the classical mechanics, which you know as a Newtonian mechanics, lies in the way they describe the physical world or the physical phenomena. So the basic difference is how they describe, how the classical mechanics or the Newtonian mechanics describe a certain phenomena which is happening in a physical world, and how the quantum mechanics describe the same phenomena in the physical world. As you know that in classical mechanics, we can predict the future history of a particle or of an object in a very determined way by its initial position. So when we know its initial position, its initial momentum together, and when a certain force is acting on a particle, then we can, with completely determined way, we can say that what will be the future of that particular particle. Okay, so for example, we have certain Newtonian equation of motion that we have v equal to, sorry, say we have v equal to, I can write v naught plus at, and say another equation that r equal to, say I can write r naught plus v naught t plus half at square. So these two equations, you already know that. So when I know that this is v naught is initial velocity, r naught is its initial position of a certain particle. So these are at time t equal to 0, let's suppose. So when I say at time t equal to 0, v naught is this and this r naught is this much, I can calculate with this that what will be the velocity of that particle after some time t. So velocity comes when I apply a certain force, which you know, if F is equal to ma, if m is the mass of the particle. So if I apply a force, there will be some acceleration. Okay, so what will be the velocity of this particle after time t, and I can also find out what will be its position at the same time t. So in Newtonian mechanics, we completely determine the future of the particle uh, by its initial conditions, and in our everyday world these quantities can all be determined well enough for the prediction of Newtonian mechanics to agree with what we find. But how the quantum mechanics describe everyday phenomena? Basically, it is not. In everyday phenomena, the quantum mechanics or classical mechanics predictions, or the classical mechanics, it's more complete than to quantum mechanics. That is different story why it is so. Uh, but the quantum mechanics also arrives at relationships between the position and momentum, velocity, all those observable quantities also arrive as the relationship between these observables. But what is the difference is that in quantum mechanics, there is no certainty about anything. It's always uncertain. There is called uncertainty principle in quantum mechanics. So in quantum mechanics, the kind of certainty about the future characteristics of classical mechanics is impossible because the initial state of a particle or an object cannot be established with sufficient accuracy according to the quantum mechanics. So when we don't know the initial state of the particle with sufficient accuracy, so we cannot predict the future with completely deterministic way for that particle. Okay, so the quantities whose relationship quantum mechanics explore are the probabilities. So in quantum mechanics there is no certainty. We just talk about the probability of finding something. For example, uh, the radius of the electron's orbit, you can see in this picture the radius of the electron orbits, like this is r1 is the ground state, this is n equal to 1, this is n equal to 2, r2 next higher level, this is n equal to 3. So these are r1 r2 r1 r2 and r3 are the radius of the ground state, first excited state, n is equal to 2, and higher state n is equal to 3. So according to the Bohr's theory, the radius for the Bohr's orbit is like this is rn. So if I radius of the Bohr's theory is in its ground state, I would like to this is r1 will be, if you put n equal to 1, because n equal to 1 here and is equal to 1, so this is basically 5.29 into 10 to the power minus 11 meter. So the radius of the Bohr's orbit in the ground state of hydrogen atom is always 5.29 into 10 to the power minus 11 meter, is always, according to the Bohr's theory, which is not a quantum mechanical theory. So Bohr theory does that the radius of the Bohr orbits in the ground state will always be exactly 5.29 into 10 to the power minus 11 meter. But what the quantum mechanics tells about this? The quantum mechanics states that this is the most probable radius. This is the most probable radius, not like in the Newtonian mechanics that this will always be 5.29 into 10 to the minus 11 meter. Quantum mechanics states that this is the most probable radius of the electron's orbit in the ground state. So if we do a suitable experiment to measure the ground state radius of the electron orbits in the hydrogen atom, so if we do it many times, so every time if you will try to measure the radius of the ground state of the electron's orbit in the hydrogen atom, it will yield a different value. It will either larger or smaller or exactly this much, but the value which is most likely to be found will be 5.29 into 10 to the power minus 11 meter. This is how the quantum mechanics describe the ground state of the electron's orbit in the hydrogen atom. So always there is a probability. There's no certainty in the quantum mechanics. What we're looking for, what we look for in quantum mechanics is always the probability. What we explore is always the probabilities of finding something. Okay, so that's what the uh, basically, however, classical mechanics turns out to be an approximate version of the quantum mechanics, because the certainty in of classical mechanics are basically not real. They are illusory, and their apparent agreement with the experiment, because when we do the experiment uh, to find the like for example to find the radius of this ground state electron orbits in the hydrogen atom, this comes out to be probabilistically to what the classical mechanics predicts. So the certainties of the classical mechanics, which are in agreement with the experiment, why it occurs then? It occurs because the ordinary object in our daily life consists of so many individual atoms. So what we are experimenting is we are experimenting with the hydrogen material. We are experiment with certain metal, not with the individual atom. So that target at which we are trying to measure is consist of many individual atoms. So what we are measuring is the overall behavior, not the behavior of the individual atom. So at quantum mechanical level, this there are many atoms at the surface, and one of this atom is this hydrogen atom, and we are trying to measure the radius of this. And classically, what we are measuring is measuring the behavior of this. So we have this consists of many atoms. We are not measuring the behavior of individual atom. This is an ensemble of many atoms. So overall, what we are measuring is not what we're measuring is not the individual atoms that actually depart from the average behavior and that are unnoticeable. So we are in individual atom, the deviation we are not measuring. So the little deviation we are as an average are being neglected in the classical mechanics, and that's why the overall agreement with the experiment in our daily life is is in agreement with the experiment. So the overall the difference between the classical mechanics and the quantum mechanics, it lies in the way that they describe the physical behavior of the nature. So I think you must have uh, some flavor of the quantum mechanics, the difference between basically the difference between the classical mechanics and the quantum mechanics. Now we'll move to what is quantum mechanical wave function. Now let us discuss the quantum mechanical wave function. So in classical mechanics, you have gone through many wave functions like the water wave, sound wave, light wave, waves on a string. You write all these waves, the mathematical representation with certain function. Function means when you give certain input and you finally get an output. So the quantity with which the quantum mechanics is concerned is the wave function, which is represented as mm, symbol psi. So this is a wave function of a body. And what is this? What is this psi? Actually, this psi has no physical interpretation. This has no physical interpretation. What this actually means? Then what is psi? So let us try to discuss what is psi and what is it is meaning by it has no physical interpretation. If we consider an electron in wave particle duality, we have discussed de Broglie wave function, de Broglie waves. So if we consider an electron, if I have an electron and if a wave associated with this electron is moving, there will be a de Broglie wave associated with this. Okay, moving in certain direction, and this is going to have some wavelength, which is Planck constant divided by the momentum m the p. So this de Broglie wave uh, of an electron is which makes the matter wave is represented as psi, the wave function. But let's say it's moving in x direction. So I suppose this is a function. So this is a function of x is moving in x direction. So what does it mean by psi x? How to represent psi x? So like in the water waves, the quantity that varies periodically, we know, is the height of the water waves. Similarly, in sound wave, it is the pressure which is varying periodically, and in light wave we know that electric and magnetic fields are varying perpendicular to each other. But what is that varies in case of the matter wave? What is varying in case of this wave, which is the matter wave when electron is moving? What is varying in this case? So the quantity whose variation makes up this matter wave is called the wave function, which is represented by this psi. Okay, so the quantity which is varying and which is making up this wave function, this matter wave, not wave function, this matter wave, is psi. So psi is varying in this matter wave. So the value of the wave function associated with the moving body at a particular point xyz in a space and at time t related to the likelihood of finding the body there at the time. So if this is if this function psi x is the quantity which is varying in a space at a particular point in xyz and at the time t, and which is giving is and which is related to the likelihood of finding the body there at time t. So what does it actually means? And the wave function, okay, forget about, but this wave function psi, this wave function psi itself has no physical significance, no direct physical significance, because the simple reason why psi cannot be interpreted in terms of an experiment. That what what do I mean by saying that it cannot be interpreted in terms of an experiment? That experimentally we cannot measure psi. Why? Because this is a quantum mechanical wave function, and then is that quantum mechanics always deal with the probabilistic nature. It always measures the probability. So the probability that something be in a certain place. So if I am saying that this psi is representing as the likelihood of finding something in a space at xyz point and at time t, then if I trying to experimentally find out, then experimentally in quantum mechanics we will try to find out the probability that something be in a certain place at a given time must lie between 0 and 1. So because the probability could be either 0 or 1, okay, between 0 and 1. So if it's 0, the object is definitely not there, and if it is 1, the object is definitely there. Or one can have some intermediate probability, say zero point 0.2. So if the probability say is zero point 0.2, it means that there is a 20% chance of finding the object. But the amplitude of a wave can be negative as well as positive. So when I'm saying that this is a wave, so when I'm saying this is a wave, some kind of wave, then its amplitude will be negative as well as positive as well as negative. So if this is representing psi x, okay, and this is x. So if I trying to measure experimentally this psi, then this value could be positive and this could be negative. So the value of is zero point 0.2. So negative probability is something which is meaningless. Okay. Therefore, the psi by itself cannot be an observable quantity. So when I say that psi, which is varying in a matter wave of this electron when it is moving, and it represents the location of this electron in a space at xyz and at certain time t. So if I try to experimentally measure this wave function, this matter wave of psi, this psi particular psi, so that means quantum mechanically I'll try to measure the probability. So probability could be positive and negative. Okay, so positive probability, like it's good, like 20% is zero point 0.2, it's 20%. But we have a negative probability also, which is meaningless. So therefore, the psi has no physical significance. We cannot measure psi experimentally. The concept of this psi was given by the Erwin Schrödinger, in I think in 1926, and he gave the Schrodinger equation we will discuss is about later, that is h squared by 2m. This is del square psi by del x square plus some v psi equal to ih cross del t over psi. This is one Schrodinger equation. So Erwin Schrodinger gives this Schrodinger equation, and if we solve this differential equation, what we get is psi x. Okay, the expression for psi x. So whenever we have a matter wave, how to find the value of psi? So we solve the Schrodinger equation given by the Erwin Schrodinger, and we get psi. So we plot psi, it comes out to be like something like this. This is my psi x, and this is this direction. So what it actually means that this particular object or this particular electron whose psi is this is varying like this. So finding this particular electron through this psi. Although we can speak of the wave function psi that describe a particle as being spread out in a space. So Erwin Schrödinger tried hard to interpret this wave function, that whether this electron is spread out in a space, or the charge of this electron is spread out this in a space which is not physical. So although we can speak of the wave function that describe a particle as being spread out in space, this does not mean that the particle itself is thus spread out. It doesn't mean that the charge of the particle is spread out in the space. Okay, so when we do an experiment to detect this electron, for instance, a whole electron is either found at a certain time and place. So for instance, the whole electron can be found at this position. The finding probability is maximum at this. Some probability is there, this is also negative. Some probability is there, some probability is there of finding the electron. No probability is here, lesser probability at this position. Similarly, some probability of finding this electron is here. So when an experiment is performed to detect electron, so the whole electron either can be found at this position, at a certain time. So there is no such thing that at 20% of the electron is here and rest of the 80% of the electron is here. That means the electron itself or the charge of the electron itself is not spread out in space. Okay, so either the whole electron is here, or either is here. It's not that 20% of the electron is here, 80% of the electron is here. Okay, its probability of finding is 20% here and 80% here. So but the moment you catch the electron, it becomes at this particular position, then it's become a particle. You can learn that. Then while other electron 80% here could be here, or 20% could be here, this is the wave nature of the electron. But the moment you detect the electron at a particular position that it is here, it becomes a particle, that it is exactly at this position. But what about this negative part? Erwin Schrödinger actually tried to explain like this, that, and he named it as a charge density, so which is spread out in a space, which is basically not physical. Then the interpretation of the probabilistic nature of the wave function comes from the Max Born in 1927. And what he says that uh, it's not the psi, it's basically the psi square, which is the probability density is important, is a real thing, is a physical thing, not the psi. Because we're talking about the probability of finding the electron or object is physical when we try to find experimentally the value of the mod psi square. So, so this particular psi itself cannot be an observable quantity. So this electron does not apply to psi square. The square of the absolute value of the wave function, the square, this is the square of the absolute value of the wave function of this psi, which is known as the probability density. And this gives the probability of experimentally finding this electron described by the wave function psi at a point xyz at the time t is proportional in the value of psi square there at time t. So this psi square is giving you the probability of experimentally finding this electron whose matter wave is described by this wave function psi at any point in a space xyz at time t. Okay, so if we try to see this, let's try to explain this, because we know sine and cosine function. So let's do it. If we plot the sine, let's plot the sine function. This is my sine function. Okay, cos sine 0 is 0. This is my sine function. This is my psi x. So this is x. Okay. So now if I plot the psi square, so let's on this axis, this is square of the absolute value of psi square, and then on this axis again we have x. So how it will look like, this will look like mm, hmm, like this. This is psi square, this is my psi, and this is square. So now you know that psi square is physical quantity, that if I experimentally try to find the psi square of this electron, so this will be either electron finding the electron at this point is maximum, or at this point is maximum, basically at this point and this point will be slightly less, here it is 0, or here it is 0 probability, here it is maximum probability, here it is maximum probability. So psi square is giving you the correct interpretation about uh, finding this electron whose matter wave is represented with psi. What is I can explain that uh, I've already told you that the large value of psi means the strong probability of large value gives you the strong probability of finding the electron, while a small value of psi square, large value, and or this is, if you find this is a small value of finding, this gives you a lesser probability of finding the electron, as long as the psi is 0 at this position, so the electron is not at this position. uh, However, there is a definite chance, however small, but the electron is there somewhere. This is definite. So once the electron, we tag the electron that this electron is here in a space, and it becomes a particle nature, and in the probabilistic nature, and the during the process of finding this the position of this electron, like this psi square, it is behaving in a wave nature. So this is wave particle duality. The moment I uh, pinpoint the electron, it becomes a particle, and when I am doing the experiment in order to find it, so either it could be here, there is certain probability, could be here, it's not here, could be at this position, could be here, could be here somewhere, could be here. So this is a wave nature of the electron. So this is what de Broglie hypothesis was, that any material particle, when it moves, a wave is associated with it, and that wave is what? It's a quantum mechanical wave function. The interpretation was given by Erwin Schrödinger, but in terms of the psi, which was not having a certain physical interpretation, but the real interpretation in terms of the probability density was given by Max Born in 1927, which actually gives the probability of finding the object or particle at certain point in space at xyz at certain time t. So now we know the wave function, quantum mechanical wave function, which is represented by this by the symbol psi. uh, is the quantity in which we deal everything in the quantum mechanics, which itself has no physical interpretation, but it contains all the informations for a body to whom it describes. But all those informations which are hidden inside this wave function psi related to that system is only measurable experimentally when we talk about the square of when we talk about the uh, square square of the mode of this wave function psi. So finding this wave function is the problem of quantum mechanics, and this holds all the information for a body to whom it describes. So in order to find all this information, we need to find the square of the mode of this wave function psi. And this is what this is we know as this is basically the probability density. Okay, so what will be the mathematical expression for the wave function? So wave function are usually written in a complex manner with both real and imaginary parts. So this you can see this is a wave function psi. This is a plus ib, where a and b are some real functions. Okay, and we can write the complex conjugate, which is psi star. This psi star is a complex conjugate of psi. So when we write the complex conjugate of a wave function or any complex number, then we replace I to minus I. So the psi star, you can see that here to here I is replaced by minus I for a complex conjugate. So psi square is multiplication of complex conjugate psi star and the psi. So if we multiply this, a plus ib and a minus ib, so this is what we get is a square minus I square b square, and this since I square is minus 1, so this becomes a square plus b square, because I here is okay, I is basically defined as under root minus 1. So therefore psi square, which is psi star psi, is always a positive real quantity as required in the quantum mechanics, because this is a square as b square. This a and b are real functions, so the ultimately the psi square, the square of the mod of the wave function psi, is a square plus b square, which is a positive, always positive real quantity. So why we need a positive real quantity? Because in quantum mechanics we are dealing with the probability density, and the probability has to be always positive, cannot be negative. So therefore for a complex psi, therefore for a complex psi is therefore taken as the product of psi star psi of psi, which is multiplication of psi in and its complex conjugate psi star. Fine. So normally the wave function This wave function, the same wave function, is represented mathematically as a complex number. This is some a plus ib. Okay, so now what we know is a quantum mechanical wave function psi, which represents the matter wave or de Broglie wave associated with any matter particle, but it doesn't have any physical interpretation. So in quantum mechanics, we usually try to find the wave function psi for a system to which we are dealing with, and then it holds all the information for the dynamics of the system. And when we find the square of the mode of this wave function, which is describing that particular system, and then out of this we get some probability density and many other things we can find out. Mathematically, we define wave function as a complex number, and the mode of psi square is complex conjugate multiplied by the wave function. So finally we get a positive real quantity as a mod square of this wave function. Now let us discuss the normalization. Uh, Normalization. Okay, what do we actually mean by the normalization in quantum mechanics? So if we consider a wave function psi, which describes, if we consider some wave function psi which describe any system, then this wave function psi must always fulfill certain requirements. And one such requirement is that this wave function, this wave function must be normalized. Normalized. So the one of the requirement that this wave function which describe any quantum mechanical system must be normalized. So what normalization means actually? We know that psi square is the probability density which basically gives the probability of finding the body which is described by this wave function psi in a space at xyz at any time t. So if we try to integrate this mod square, if we try to integrate this mod square minus infinity to plus infinity psi square dv, then what should be on this side? So dv here is basically dv is like dx dy dz. Okay, So integrating over the whole volume from minus infinity to plus infinity. So this, if we integrate the probability density over the entire volume from minus infinity to plus infinity, so this side must be a finite number, a finite number. What does it means that the integral of psi mod square over whole space from minus infinity to plus infinity must comes out to be a finite number? What does it means? It means that the body to whom we are describing by the wave function psi, this wave function psi is somewhere in the space from minus infinity to plus infinity. If I write this minus infinity to plus infinity, this mod square psi dv is 0, then what does it mean? It means that particle does not exist. That means this wave function which is describing the particle is actually does not exist. But if I am telling that this wave function psi is describing a particle, so if I integrate the mod square from minus infinity to plus infinity over the whole volume, then it cannot be 0. It cannot be equal to 0 because it will tell that the particle does not exist. Similarly, if you write this minus infinity to plus infinity, this mod square psi dv, if I tell that it is infinity, it doesn't mean anything. What do you mean by the probability of finding the particle in a space from minus infinity to plus infinity is infinity, because probability cannot be infinity. So it's absurd to saying that this is infinity. It is also wrong. Further, if I write minus infinity to plus infinity, psi squared dv is some negative quantity, negative number. So this is also not true because the probability cannot be negative. So it cannot be 0, it cannot be infinity, it cannot be negative. It has to be some finite number, which represents that the particle to whom this wave function is describing is somewhere present in the space. Okay, so the only possibility left is that the integral be a finite quantity if psi is to describe properly a real body. So it is usually convenient to have psi square to be equal to the probability density of finding the particle described by this wave function psi. So if psi square is equal to some finite probability, then we can write that this minus infinity to plus infinity, this psi square dv is equal to 1. And this process is known as normalization. So since if the particle exists somewhere at all times, we can represent this also as minus infinity to plus infinity. We can write p dv equal to 1 because this mod psi square is represented as p probability somewhere. So this is 1. So this process of finding integral from minus infinity to infinity of the wave function psi describing a system integrating over the whole volume and putting it equal to 1 is known as the normalization. And the wave function, the corresponding wave function is known as the wave function. Normalized wave function. The process is the normalization, and the wave function is said to be normalized wave function. So if we do the normalization, this minus infinity to plus infinity, this is psi square dv doesn't come to 1. If it comes to half, then what we do is, like, we redefine the wave function as some wave function, say psi 1 or psi naught, and this is equal to 1 upon root 2 of this psi. And then we can find this minus infinity to plus infinity psi naught star dv. So this will comes out to be 1 by 2 minus infinity to plus infinity psi square dv is equal to half, and then this gives you minus half to plus half psi square dv is equal to 1. So this is how we normalize a, a wave function if the wave function is not normalized. So this process is known as the normalization, and the wave function satisfy this condition, then this is said to be a normalized wave function. So every acceptable wave function can be normalized by multiplying by an appropriate constant, like we have multiplied it by a constant 1 upon root 2. So this is the process of normalization, and the corresponding wave function is said to be a normalized wave function. Now in the next slide we will discuss the further requirement of wave function. So this is the normalization or normalized wave function is one of the requirement if this wave function psi is basically representing properly or describing properly a real body. The next requirement for a quantum mechanical wave function, beside being normalizable, uh, if you see the first condition that psi must be continuous and single valued everywhere. So psi must be continuous. Check it. psi must be continuous and single valued everywhere. The second condition is the derivative of the psi must be continuous as well as single valued everywhere. The third is psi must be normalizable, which we had discussed it in the previous slide. Normalizable, which means that psi must go to 0 when x, y, or z tends to plus minus infinity. And why it is important that psi must go to 0 as x, y, and z goes to infinity. So in order that this psi condition of the normalization over all space be finite constant. So these three conditions, first, second, and third, that psi must be continuous and single valued everywhere, its derivative must be continuous and single valued everywhere, and psi must be normalizable. These three conditions are must for a well-behaved wave function in order to represent a physically meaningful result for a system when we used to calculate certain properties for the system. Okay, now let's try to understand what these three requirements actually mean. So if you see the first requirement, the psi must be continuous and single valued everywhere. So you can see that I have taken an example of this, say y equal to cos theta, y equal to cos theta. So I can say my wave function is nothing but this is psi, and on this axis, say this is because this is x, psi x is nothing but is, I say this is cos x. Okay, so we know that this is a function, the psi is a function and which is continuous and single valued. So if we plot psi cos x, so this you can see this is what my cos x is. Okay, so this is, now you can say that this is continuous and the single valued function. That means for each value of x, so if you concentrate on this curve only, so for each value of x, like for this value of x, there's only one value corresponding to psi. Okay, similarly for this value of x, okay, and there is only one value of psi, which is this thing. Okay, so this is what we mean by a single valued function. Like you can see here in this graph, uh, in this graph you can see this is this first graph. I can represent this graph psi x, this psi x as is, if this is a constant, this is 1, psi x is 1. So this is a straight line, so this is continuous and single valued because this is constant. For each and every value of x we have a single value, only one value, 1. Okay, similarly, so this psi equal to cos x is continuous and single valued. Now its derivative, if we find the derivative del psi upon, because in terms of del x, so this becomes minus sin x. So we know that this, if we plot the sin x, so this is sin x. Okay, so this is my sin x. So now you can see that sin x is also a continuous continuous as well as a single valued function. Okay, so for every each value of this, if say this value of x, I have only one value of sine x, tk del psi by del x. So the wave function psi x is cos x, which is continuous and single valued. Similarly, its derivative, which is sine x, is also a continuous and single valued everywhere. So these two conditions, first and second, are fulfilled by this wave function. Okay. Now, it's the same thing you can see here in all these graphs. So let's just try to find. If you see this graph is psi equal to 1. If we try to find del psi by del x, this will be 0 because this is constant. So this is also a single valued function, not a constant, but doesn't mean it's a single valued everywhere. Similarly, if you see this graph is not well behaved function, because for a single value of x, if you draw a line, I have two value of psi x, this value as well as this value. So it's not a single valued everywhere. Also, at this position, at this point, it is discontinuous. So the psi is not continuous as well as it is not single valued function. So this is not a well behaved function. If you concentrate on this, so this is like this is a continuous and single valued everywhere, but at this point the derivative will be discontinuous. So derivative, the second has point tells the derivative must be continuous, but at this point derivative is discontinuous. So this is also not a well behaved function. This is okay, this is continuous and well behaved. This is also okay, but this is not okay. So this is discontinuous at this position, it's continuous at this position. So this is not good, this is not correct, this is not well behaved function, this is well behaved function. This is also not a well behaved function because this will leads to infinity. This is okay, this is also not good because this continuity is there. Similarly, this is fine, this is not good because it is a too continuous, but you have not a single valued function. For one value of x, we have three value, one value at this position, one value at this position, one value at this position. This is not a single valued function, so this is not acceptable wave function. This is also acceptable wave function. So now you know that for a well behaved function, psi must be continuous and single valued everywhere, and its derivative must be continuous and single valued everywhere. So third condition is psi must be normalizable. Normalization conditions, we have seen that uh, when we write is minus infinity, integrate from minus infinity to plus infinity, the wave function psi square dv over all space should be a finite constant. Okay, a finite constant normalization means it should comes out to be 1. Okay, so which means that psi must go to 0. Why psi must go to 0? It is asking that the psi must tends to 0 as x tends to plus minus infinity. Okay, so why, or y tends to plus minus infinity, or z tends to plus minus infinity? Because dv, we are integrating over dx, dy and dz. If this condition is not hold good, that psi tends to 0 and xyz tends to infinity, then what will happen? What we are doing is we are integrating over all space from minus infinity to plus infinity. So if some wave function, integrating means what? Integrating means we are calculating the area under the curve. If this is my psi, so integrating this with psi is calculating the area under this curve. So if I integrate this from minus infinity to plus infinity, and if this wave function when x or y or z is tending to infinity, and if psi is not tending to 0, okay, the psi is not tending to 0, it's going to some value infinity, okay, then the area will not come to a finite constant. So if some curve is going to infinity, then the area under that curve will also tends to infinity, which we don't want to be a normalized function. So that's why psi must tends to 0 when its dependent variable is tending towards plus minus infinity. Otherwise, the integral will not come to be a finite constant. Okay, so this is what we need for a well-behaved wave function, well-behaved quantum mechanical wave function. The next thing I, I would like to uh, tell about is the probability. Okay, probability. Okay, how we define the probability. So, given a normalized or otherwise acceptable wave function psi, if I have been given a normalized or if I say is acceptable wave function, if the wave function is acceptable, that is already normalized. So if my psi is acceptable wave function, then the probability that the particle to which this wave function psi describes will be found in a certain region in a space uh, is simply the integral of the probability density. Integral of the probability density psi square over that region in which we are trying to find that particle to which this wave function describes. Therefore, if a particle is restricted to a motion in suppose in x direction, the probability of finding the particle between two position x1 and x2 is given by, if I integrate between x1 and x2, integrate the psi, so this quantity is known as probability of finding the particle. If this particle is traveling along x direction, then what is the probability of finding the particle between the two position x1 and x2 when this particle is defined by the wave function psi? So integrating the square of the modulus of the wave function between these 2 points x1 and x2 integrated over dx will give you the probability of finding the particle between these two positions x1 and x2. Okay, so this is how we define the probability of finding the particle. Okay,